Welcome to the next in the short series of videos about noise. In this one I want to talk about probably the most common error that people make when they first start dealing with noise. How to add up two different noise sources. First of all, let's look at a more familiar problem. Adding up two sine waves. If I have a sine wave here, which has a peak-to-peak value of 2, so it varies from 0 to 1 down to -1 and so on, and I take another sine wave, which is in phase with the first one, and also has a peak-to-peak value of 2, add them together, and I end up with a sine wave with a peak-to-peak value of 4, from -2 up to 2. 2 plus 2 equals 4. Fair enough. What about noise? Well, if I take a noise waveform, this one has an RMS value of 1, and add another noise waveform with an RMS value of 1, what do I get in the answer? Well, it's likely not to be a noise with an RMS value of 2. To get that, you would have to double the size of all of the peaks and the troughs in this noise, and that's very unlikely. That would mean that when this noise was high and positive, the second noise signal was also high and positive, and when this noise was low and negative, this noise would also have to be low and negative so that the two would combine. That's very unlikely to happen. So how do we add together two noise sources? Well, we can try this in the simulator. Here we have a DC circuit on the left and a noise circuit on the right. The DC circuit has two 1-volt voltage sources in series, so if we add them up, the answer is going to be, for the voltage across the whole thing, 2 volts. Not a surprise. Over here we have two noise sources, both of which are 1 volt RMS per root hertz, and if we add them up, then the result shown on this voltmeter here is going to be 1.414, or the square root of 2. Why the square root of 2? Well, for that we have to do a bit of maths. Consider what happens when we have two independently varying noise sources. I've called them Ni of t, that's one noise waveform, might look something like this, and Nj of t, that's another noise waveform, not the same, might look something like this. If I want to know the average power in the noise signal which is the sum of these two, then what I'm interested in is Ni of t plus Nj of t, that's the actual sum of these two waveforms, squared, and what's the average value of that? And that will be the mean power in my noise. The mean voltage in the noise is just the square root of the mean power. So what's this? Well, if I multiply out this bracket, I get Ni squared of t, average, plus 2 times Nit Nj of t, average value of that, plus Nj squared of t, and I need the average value of that. And I'm using the fact here that the mean value of the sum of 3 terms is the sum of the mean values of each of the terms, which is generally true. Okay, well, Ni squared of t, that's just the noise power in this first signal here. Nj squared of t, that's the noise power in this second signal here. This term in the middle, however, well, that is the average value of twice the product of these two noise voltages. And the interesting thing about this term here is that it's 0. Why is it 0? Well, Ni of t and Nj of t are independently varying noise waveforms. They are each positive half the time and negative half the time. So, in terms of whether they're positive or negative. They could both be positive. Ni of t could be positive when Nj of t is negative. Ni of t could be negative when Nj of t is positive, or they could both be negative. If they're both positive, then the product is positive. If they're both negative, then the product is positive. But if they have different signs, then the result would be negative. So the product there is positive half the time and negative half the time. And if it's positive half the time and negative half the time, then on average it's going to be 0. So the mean power is just the power in the first waveform plus the power in the second waveform. In other words, if we're adding noise sources, we need to add their powers. The mean power in the sum is the sum of the powers in each of the two sources. In terms of the RMS voltages, we know that the voltage is the square root of the power, so the RMS voltage of the sum would be the square root of the square of the RMS of I plus the square of the RMS of the noise source J. We take the RMS voltages, square them, take the square root of the sum of those, and that is the RMS voltage of the resultant noise. Key takeaway thing to remember: if you're adding noise sources, always add the powers, not the amplitudes. Right, that's all I wanted to say this time. Next time we'll have a look at where noise comes from, what circuit components actually contribute noise, and how much.